Hello, everybody. It's good to be back here. I've been here for a couple of Go meetups and Redis meetups. It's a wonderful place to be. Also, I didn't know you can do shout-outs about positions. So we are hiring for developers, especially with Redis experience. So think about it. So I am going to talk about Redis today. First, a little bit about myself. I've been at Twitter since late 2010, so that makes me one of the old-timers. The entire time I've been on Cache Team, so I always get the question, why are you still on Cache Team? So the answer is I'm still on Cache Team. And I've been working on TWM Cache since the beginning, and I picked up Redis because nobody else, well, Cache is the right place for it to be. And I've worked on development also, as well as capacity, deploy diagnosis, because for about 2 years we didn't have any SREs for the Cache team. So I was basically an SRE as well as a software engineer for about 2 years. And then we got properly equipped so people don't have to look at my terrible, terrible scripts. First I'm going to talk about how we came into using Redis. I'm probably preaching to the choir here because everybody here knows how wonderful Redis is, but I just want to give you concrete examples of how we started using Redis. So as you may or may not know, Redis actually drives Twitter's most important service, timeline. So think of timeline as just an index of tweets, right? Each tweet is represented, can be indexed by a tweet ID. And if you chain them together, then you have your home timeline as a list of tweets, and your user timeline, which are the things that you post or retweet, as another set of tweets. So that's actually driven by Redis. So one thing, before that, we were using Memcache to store timeline, but the problem is, whenever a new tweet is generated, you want to fan out to all the relevant timelines. So you will attach this very small piece of data to something, and when you read, you probably want to load just a small batch of tweets, and when someone scrolls down, you load some more. Right? So all the reads and writes are actually happening incrementally, and they're fairly small. In comparison, the timeline itself can be fairly large. Your home timeline, we may want to store up to, 800 or 3,000 or whatever number that's reasonable for most users to view in one set. You don't want to go to the database for that kind of thing. So the dilemma here is that we have small reads, small writes, but the object itself is fairly large. So when we do read, modify, write, we actually are sending all these very large objects for very little work. So that's one thing that makes us realize, this is too expensive. We want something that doesn't introduce the network bottleneck. Because if you have a gig link, and as most cache services, TWM Cache, Redis, when they do simple reads and writes, they can do way more than 100K a second. So if your average object size is more than 1K, now the bottleneck is on the network. You don't want that to be the case. A second case that's common is that we have this long common prefix problem. So I'll give you two examples. One is you have a flexible schema. You have an object that has certain attributes that may or may not exist. So you can create separate keys for each individual attribute, but you need to send out individual requests for every single one of them. And you don't even know if you get all the attributes because they may or may not be present in cache. They can be evicted. A second problem is, think about, say, metrics that gets observed over time. So all the metrics actually have the same name. The only difference is that they will come with a different timestamp. So when you store those things, if you want to store them in cache, if you store them individually, you're actually repeating the very long common prefix many, many times. Depends on how often you want to keep the metrics in cache. So in these cases, it's actually very much desirable to have everything under this long common prefix so we can be more space efficient. So these are the reasons why we started considering Redis. And on the other hand, we did notice that for anything that's like in-memory key value store like TWM Cache, or if you use Redis for simple cases, it's actually fairly CPU light. So in our benchmarks, usually 1% CPU time can handle more than 1K requests per second for small key values. So a dedicated in-memory caching cluster actually are always underutilizing their CPUs. This is not considering data structure, that's a different story. So basically, if you just do simple key value, there's a lot of room on the server side. So it's actually, I think Redis is a brilliant idea, it sees that, what the server can do, but it's not doing, and makes a service out of it. So I think it's a great insight, and that makes sense. So we decided to use Redis. And I use this picture because even though we've been using Redis for a few years, the work we've done around Redis is like a construction site. We have several attempts to make several projects out of basically Redis as a cornerstone, but we don't have a grand mansion, like this is the one service that we build on top of Redis that does everything. We don't have that. So the things I talk about a bit later about what we've done with Redis is going to be a little scattered over the place, because we still have a lot of work to do in this space. So a few facts. We took our first stab in 2010. I should not take the credit for introducing Redis to Twitter. So people working on real problems actually found out about Redis. The timeline people, they were like, this is great, we should use this. So the timeline people were the ones that introduced Redis to Twitter. And the production launch of Redis with Timeline is in fall 2011. And the code is actually released under this project, Haplo. It's a made-up dinosaur. It doesn't exist. Today, it drives our timeline, and it drives also our revenue. I cannot talk about the revenue side because the project is not released like Haplo, but I'll talk about the concept. We use Redis strictly as a cache. We don't use any of the on-disk features. Someone has said, the structure of the code of a company reflects that of the organization, and you can tell, cache and storage for the longest time have been two different teams. So, but there are legit reasons on top of that we are not using Redis for storage, because there's a lot of quirkiness and different, goals you want to achieve with storage, and we have a very good team for that as well. So we leave this storage tier to them. And the versions we used were 2.2, which was new by the time when we first looked at it. And later we forked off 2.4 and added a bunch of features on top of it, and that's why we are kind of stuck with 2.4. But I do have a pull request that awaits company approval. I hope to merge some features back to trunk. And so the changes we did mostly consist of 2 data structure features that's within Redis itself. We also have several in-house cluster management for Redis, because everybody knows Redis cluster is hard, but it's necessary. And we also have in-house logging and data insight, which I will cover in a bit. So let's first look at the data structure features. I want to give you the motivation first, why we wanted to introduce an improvement of the data structure. So going back to timeline. Timeline basically is a list of tweet IDs. So think of it as just like a list of integers. So every tweet ID is fairly small, and as you all know, in Redis there are 2 types of data structures used to implement a list. One is zip list, that is very space efficient. There's very little overhead per key. And the other one is linked list. So linked list is very flexible. It's very cheap to insert and remove nodes, but it is implemented as a doubly linked list. So you pay several pointers, at least 2 pointers per key. And that, if you're storing just the integer, is actually quite considerable overhead. Right? Basically, your metadata is several times the size of the data you're storing, which is just an integer. So this means for us to use the memory efficiently, we basically are stuck with zip list. And what we did actually is to just ban the use of linked list by setting an upper bound of how big the timeline can be. So we set the Redis instance, the threshold accordingly. So we never store a bigger timeline than what the Redis can hold in the zip list. So in some sense, from an architecture point of view, this is kind of a leaky design, because now you have a product decision, which is how many tweets you can store, linked to a very low-level component, which is how do you configure a Redis instance. Right? So and that's not the only problem we have. So when you update zip list, if you are deleting something, you're moving actually a bunch of data around. You do man move to make sure the list is still contiguous, right? And when you do an expansion, you need to do a realloc, so you have enough space. So these, when you have a very large list, are actually can be fairly expensive memory operations. Another thing is, in our case, timelines are actually timelines vary a lot in their sizes. Most users don't tweet, so their user timeline is tiny. They have a few tweets or nothing at all. But your home timeline or some celebrities, mentioned timeline can be gigantic. So what happens is if you're trying to update or write to one of those big timelines, and the Redis has run out of heap memory, which is often the case when you use something as cache, right? You want to use all the memory and start evicting. So when that happens, you may try to evict a very large number of very small timelines before you have enough contiguous memory to accommodate this one big zip list. So not only is that, that means that particular write operation will end up having very high latency. And as what we do is we fan out writes to a lot of timelines. So the fan out factor means you have an even higher chance for your regular fan out operation to be caught in one of these write latency traps. So it's very hard to come up with a reasonable SLA when you know your eviction can be potentially be very expensive. So that's the thought behind hybrid list, is that we still want the memory efficiency of zip list, but we want to have more predictable memory allocation and reallocation performance. So the idea is really simple. It's just like you have a linked list of zip lists. You set a threshold of how big each zip list can be, which is in terms of bytes, not items, because if you want to aim for a memory efficiency, you want to allocate and free memory chunks of the same size. That's the most efficient. And when the list goes over, you just spill over the extra into the next zip list. So one gotchas is that if you do a lot of deletes, potentially one of these zip list chunks can shrink. So in the very worst case, you may end up having basically like just a linked list, right? If you delete all but one items from every single zip list, you may end up with a situation like that, because we don't recycle until a zip list in this chain is empty. But in practice, because most people don't actively delete their tweets all the time, it's not a common case. Also, it can be mitigated if you optionally add a merger function when you delete. But so far, we don't have the need for that, so that's still void. So that's the first thing, is hybrid list. It gives us very predictable memory performance. And so before we had hybrid list, one mitigation method we had was we would actually expire larger timelines more quickly. So when something comes around, it's more likely to have an expired large chunk of memory sitting around to use, which is counterintuitive, because why would you want to evict something that's more expensive? But basically, we had to do that until we have this. So that's the first thing, first change we introduced to Redis backend. By the way, if you guys have any questions about any technical details, I'm happy to answer, and feel free to ask. So here are the numbers about the use of this Redis hybrid list. So basically this is the numbers about our timeline service. We have about 40 terabytes of allocated heap. Which serves about 30 million QPS. And we have over 6,000 instances. And this is in one data center. We do have multiple data centers, but I just sample numbers in one. And these numbers are reasonably close. They are not the most up-to-date, but within a few months. And the second one is B-tree. So B-tree is really trying to do two things at the same time in one data structure. One of the things is previously I said we may want hierarchical keys for space efficiency. So in one case, we want to do kind of like a point lookup with a hierarchical key. In another case, we want to do a range query. So we want to do a range on the however you define order on your hierarchical keys and get a list of results. And the current way of doing that in Redis is that if you have like secondary keys or fields, you would use a hash map. If you want something that's sorted, so you can do a range query on it, you would use sorted set. But one limitation of sorted set is the score is translated into a double. So basically, you cannot use an arbitrary secondary key or arbitrary name for the sorting. And also, on the other hand, the limitation of hash map is hash map because it does a linear lookup. It's not really great if you have a lot of secondary keys or fields in one primary key. So B-tree is our attempt to basically fix these shortcomings of the, so we just want one data structure because that's so much easier to reason about than keeping two things in memory. So we basically borrowed the BSD implementation of B-tree. It's a fairly clean implementation and stuck it in there and created what we call a B-tree set. So B-tree set supports both point lookup as well as range query. And the good thing about that is, it has, theoretically, it has good lookup performance. The code is relatively simple. It's actually simpler than the skip list. I checked the line of code. It's actually a bit shorter. The downside of B-tree, though, is because we didn't do any memory optimizations like zip map, zip list. These are actually fairly well designed for improving memory efficiency. So B-tree actually is kind of a memory hog. It has a lot of metadata overhead associated with having all those B-tree pointers stored in memory. So we also have a pretty wide adoption of this B-tree feature. As you can see, it serves about 9 million QPS at this point, but it actually occupies more memory than the previous example. This is largely due to the memory inefficiency of the data structure itself. You can tell good, well-designed storage, data representation format makes a difference. And we have about 4,000 Redis instances allocated this way. Again, numbers are in one data center. So the second thing I want to talk about is cluster management. Cluster management, I think, probably is the #1 reason why Redis adoption hasn't exploded. If people can use Redis as a cluster, I don't see any reason why people won't migrate all their cache cases to Redis. But on the other hand, I think it's actually fairly tricky for someone to get the Redis cluster right. So kudos to the people who are actually working on it. Because Redis is perceived as a data structure server, so the use cases actually skew relatively heavily toward the right side. People can use memcache for immutable data, and for immutable data, you don't even care about data structure because you can pack the data however you want, and you just read it once, and you write it once and read it later, right? So that's not too big an issue. People use Redis because they want to update that frequently. But the thing is, a lot of Redis operations are not idempotent. So if you have a network glitch, you have to retry, or if you lose a node for a while and it comes back later online, now you have corrupted data. So actually, I think doing Redis cluster right is fairly hard. And my personal view is that Redis cluster actually favors having a centralized single view of the cluster very heavily. So in the case of memcache, there are a lot of implementations about the client-side cluster that does consistent hashing. And if you have inconsistent data, so be it. I think Redis would actually benefit a lot from having something like a cluster manager dictating the global view. And on top of that, if you want to provide really good service, you may want to do things like detect which shards are being done, and trying to even replay the operations you want on the data that go into those shards. And when those shards actually come back after a long enough period of time, you may actually want to clean up the state of the shards because you don't want corrupted data in Redis. Corrupted data in Redis is actually much harder to detect because when you have a list and it's missing a chunk, it's much harder to say this is wrong than just having an empty one. So we actually did more than one project on trying to basically build a Redis cluster. The first one, I think it's also the most well-known in the community, is Twin Proxy. This is basically Munger's project, and I think it's recommended by Redis until Redis cluster is ready. The funny thing is, Twin Proxy, as the name suggests, was not built for Redis in the beginning. It was built for Twimcache. And we actually have never used it for Redis internally. But Munju saw this problem that cluster management is really is the real thing for Redis adoption. And he was like, well, let's just add Redis support, and it proves to be a very invaluable project. So check it out if you're, if you still need it in the interim before Redis cluster is released. And we did 2 more solutions based on proxy style routing. One of them is the Haplo project that I just mentioned earlier for timeline. So this project is fairly closely coupled with timeline. It's not really a general purpose Redis cluster. We have a second solution, which is an attempt to basically generalize that and provide both cluster management and some sort of replication and shard repairing in the Redis cluster. So I have a couple of comments on why we choose the proxy style, because there are 3 options you can have here. One, you can have the server talk to each other and reach an agreement of what the cluster looks like. 2, you can do proxy. 3, you can do client-side cluster management. So it's either they form a quorum themselves, or it can be just every client for their own. The reason in all these attempts, we went with a proxy style routing and partitioning. I think there are 2 reasons. On the server side, Redis, a cache service is actually relatively high throughput compared to most of the services that's run in a just web framework. Not every service can serve like 200 kQps. So my personal philosophy is, if you want something that's high performance, you want to separate the fast path, which is the data path, away from the slow path, which is the control path. This is a term that's borrowed from networking community. So for things like cluster management, if you stuff that into the server, not only does it complicate the code, for Redis or for any caching services that's kind of stateful, the practical implication is that anytime you want to fix a bug or anytime you want to introduce a new feature in your cluster management, you have to restart a stateful service and potentially throw away a bunch of data. And anybody who's managed a cache cluster know how painful it is if you want to just do a rolling restart of your cluster. So that's basically the reason we didn't go with server, is we want to keep the server as simple, as dumb, but as fast as possible. And the other thing is, why didn't we go with client? So at Twitter, we have about close to 100 now, probably, projects using various kinds of cache clusters. If you do anything in the client, potentially you're pushing a client change to 100 users, and it would take years for all of them to adopt any change you make. So basically, in practice, if we're in this stage of just building a cluster and doing quick iteration and want to add features or fix bugs, it's almost impossible to do that in the client. So this is, sorry.
Could you clarify what you mean by clusters? Is it only sharding or replication as well?
Oh, yes. So basically, by cluster, I mean using more than one instance of Redis for a single purpose. So if your data set is bigger than what a single Redis instance can handle, or your throughput is higher than what a single instance can handle, you want to potentially partition your key space and store them in more than one shard, and then talk to them and you want to do key hashing, you want to do routing based on your setup. So that's what I mean by cluster. What was that? Yes, so client, so that's why we rule out client-side configuration. So we did have one concern about adding another layer between the server and the client, which is you introduce another network hop between the client and the server. And for the longest time, I actually am a firm believer that another extra hop in the network is bad for latency. But we did some profiling to monitor where the latency are actually coming from more closely, and turns out the extra network hop is kind of a myth. Why? Not because the network hop is free, but because of the ecosystem. I don't know what kind of ecosystem you guys are working in Twitter. So the entire ecosystem, other than some of the backend services, which is in C, C++, are mostly in Java and using Finagle to talk to each other. So Finagle is a library that's probably a lot of you would know. So Java, I would say Java, JVM-based runtimes have very different runtime characteristics. And in one case, when we were doing the end-to-end latency profiling, what we found was on the client side, if you measure latency to a cache server, the whole round trip up until the point of the kernel. So if you add a filter in the kernel, say, I'm going to collect a timestamp when this request is going through the kernel stack. And I will take another timestamp when the response comes back to me through the kernel networking stack. And you compare these two timestamps, you will find that most of your latencies, by most I mean P49, is under 500 microsecond. So that's less than half a millisecond. Although if you go look at, let's say now we zoom out, we go to the top of Finagle, which is how people issue their request. If you look at the latency there, what we found in this particular service is that we see P29 close to 10 milliseconds, which means in your tail latencies, it's your worst latencies outside of the JVM doesn't even contribute to more than 10% of your tail latencies. So it's kind of a moot point to trying to squeeze as much juice as possible outside of the JVM. You can do pretty much whatever you want. Adding another extra network hop is nothing, as long as you don't go through another similarly slow JVM. Right? So this is an example of using test-driven or experiment-driven design to come to the right conclusion and come to the right priority. Yes.
So I was wondering, besides the network hop, like introducing a proxy is introducing another possible point of failure.
Yes.
And another scalability issue.
That's right. So the answer to that is, so on the data path, introducing a proxy layer actually isn't so bad because the client doesn't really care which proxy they talk to. If a proxy fails, after the timeout, they go to another one. There's no sharding happening at the proxy level, right? They're all stateless. So it's actually fairly easy if all you want is to scale throughput, you just throw more proxies at it. So actually the trade-off is that proxy layer one is extra network hop, which we said is not a big deal. The other one is actually cost, right? Previously you can answer the request with just the backend of the client, and now you're allocating these resources in the proxy just to do the forwarding, right? So cost is a real concern, but failure of a proxy node doesn't really mean much. The reason is because we actually do cluster management, like we do all the sharding and do the view of the cluster outside of these proxies. So if these proxies has to agree with each other, that's terrible. Like you don't want an n-square algorithm or something like that, right? So you will have a global view. That global view may not be your optimal view. Like what happens if so you have to do something about it. Like what if your centric view itself is, the server itself, the observer is down, right? But there are mitigation methods for it. You can basically hold on to your cached view if you notice that your cluster leader or manager is down. So this is not too hard. It's much easier to solve actually than forming a quorum among a large number of proxies. So making a large number of nodes agreeing with each other is hard. Having one node taking care of the view and restart it or move it or reschedule it when it's done is much easier. So that's that. At least that in our experience, that has been the case.
You guys probably have like persistent connections between the proxy and the server.
Yes.
And that kind of explains why you don't see the additional latency.
Yes, I
because
think
the connections are persistent. Otherwise, you would see more.
I would say unless you have a number of connection issue, which would be very hard to achieve these days. Like we have instances that have like 100K open connections, and that's fine. It's just the overhead you pay, right? I don't see any good reason for closing connections. You just keep them open for as long as you can. We have been doing that for a long time. And we've actually seen difference in latency. Keeping long-living connections improves the latency. Any other questions? Yeah.
When you add a node, a Redis node, how does the proxy server begin to delegate data to this new node?
So we actually, I don't think any of these projects are actually released in the public. But in principle, what we do is we have an abstract layer for sharding. So think of not having keys mapping directly to physical machines, having them map to an abstract address space. And then you do the mapping from the address space to the node. So when you add a shard, the leader of the cluster actually generates a new mapping from all the abstract shards to the physical nodes, and the keys basically are moved accordingly. And the proxies, so the backend goes through state transitions to be ready to serve these newly assigned shards. By that time, the proxy will get the same update, and that's when. So basically, there's I cannot go into too much details, but basically there's a preparation stage, right, in which you make sure the backend is ready, and then the proxy can forward request.
What happens when a node goes down? Do you reload from the disk, from disk, or you have like master slave?
So far we are still using all our cache clusters as look-aside cache, meaning that the caches themselves are not responsible for what you call data replenishment, right? So it's the client, whoever is using the cache, is responsible for fetching a missing key from, say, the persistent storage and stick it in. But we do take care of, say, if a node does go down, we do take care of, we recognize this shard is down, we basically move all the address space that's associated with the shard to someone else. And we actually flush this physical machine when it comes back so we don't have any polluted data. And all this is done by what you may call the cluster leader. I actually think having a centric view is really important for keeping the cluster in a state that's easy to understand. All right. So that's basically the reason why we did proxy style routing. Also, the two solutions we came up with later, given Twitter's ecosystem, are all JVM based because all the RPC framework and all that is set up on top of Java libraries or Scala libraries. But recently, interesting thing is we did an experiment comparing what we can do with, say, a proxy implemented in C++. We actually see quite significant performance improvement. So we're on our way of actually moving the proxy tier back to C and C++, but it will be a different solution than the Twin proxy. Data insight. So earlier I mentioned for about 2 years I was basically SRE on top of software developer, actually more of a SRE than a software developer, because who has the time when you're managing 2,000 machines, right? So one thing I really hated is at 3 a.m. someone, maybe what we call TCC, which is the Twitter command center, they take care of the service, the health of the service as a whole, calls me and be like, hey, this other service is seeing degraded SLA, and their cache latencies are high. What's wrong with their system? And I look at it, it's 90% of the case, I can say, the cache system is fine. It's most likely either they're misconfiguring their clients or they're abusing the cache systems by requesting way too many keys or requesting the same key over and over again, therefore saturating the server or even the link. Right, but when you tell them, hey, you're abusing my system, they will be like, give me proof. Tell me which key is bad. Tell me which shard is getting what kind of traffic that leads to this behavior. So my personal belief is an SOA architecture doesn't give you, error isolation, doesn't make debugging easier automatically. I think the hidden premise that's not often spoken about is you have to have good visibility into every single component that makes up the whole system. So we decide that we should build insight into our component because cache is fast and we can do things very efficiently in C. We can provide data insight that other services say they cannot do. They say they cannot log all the requests. That's fine. We can do this. So that's exactly what we did. So this originally was implemented in Cache. So that's why the format, if you ever looked at Cache, it's pretty much the same, but the key structure and the commands are different because Redis is a different protocol. But essentially you have all the metadata. You have the source IP, source port, you have the timestamp, you have the command, you have the keys that are, or fields that are relevant, you have the return status, and you have the return length. So the thing we skip is we skip the values themselves, because NSA has told us, you don't need the value, you just need the metadata to figure out most of the story. So that's what we do. So two things to make logging every single command possible on a high throughput system. So we've tested this with 100K QPS. We can log everything. It's not even hard. Two things you should avoid: no locking, don't use locks. No blocking, don't block your worker. If you have to wait on a disk write to serve a request, that's terrible. Talking about which, I'm pretty sure the logging module that we have fail that two criteria. It can block requests. So that's one thing we're working on to fix. But this command logger actually doesn't block and doesn't log. So now we have 100K QPS logs per second. What do we do about it? So a simple calculation tells you if you have 100 bytes per log, which is reasonable, right? If you don't compress anything, you look at the format of the log, and you have a reasonably large key, then 100 bytes is about right. Then you will have 10 megabyte of data per second per box. Now imagine if you would have to send that logs off the box using Scribe or whatever messaging mechanism. That's actually a lot. You're using 10% of a bandwidth just for something that you will use in case things go bad. So economically, that's not very reasonable. What we did is we started doing pre-processing on the box. So the premise of this is that you already roughly know what you want to compute, which if you're trying to solve recurring problems is mostly true. So we deploy this little process that reads these logs and generates a little summary of the views that we want, and periodically send that view off of the box. Usually that summary is tiny compared to the original volume of the data. So we solve the bandwidth problem this way. And later, when we get the data off the box, we use some existing framework that's maintained by Twitter. We use Storm. We have it stored in our storage system, and we have a visualization on top of it. So we can point to people to our visualization and say, here are your top 20 keys. Right? Here's your traffic, by second. You have a peak here, meaning you have very spiky traffic pattern. Here are the number of unique keys. So if you want to plan capacity, this should be your upper bound. So there's actually quite a bit of things you can do if you actually can capture every single log. So this has been, so our SREs actually love this. So whenever we have an issue, we see, packet drops or things like that. Often we can pin that, we can link that to either a hotkey or spiky traffic behavior. So this has proven to be very valuable on the operational side. So that was pretty much all I want to talk about of what we have done with Redis. If there's any questions, now is the time to ask. If not, I'm going to move on to my personal insight. I'm terrible with cat pictures, so I go with gorilla. I have to, this is like a disclaimer. All the views here are not Twitter's view. This is my personal view. My teammates may not even agree with me, but so take that with a grain of salt. And this is more for discussion than, just preaching. First is, so I've been at Twitter for a few years. I've seen the growth of a system. I've seen cache from being used by maybe one service or few services to now like close to 100. And one thing that I feel, this is probably the number one takeaway of my experience on the team, is that I think scale demands predictability. What I mean by that is the larger the cluster, the more customers you need to serve, the more predictable and deterministic you want your service to be. It's kind of cute when you have an outlier and you run one service, you've got to dig into it and be like, hey, why is this happening? right? It's exciting, it's intriguing. When you have 70 customers, it's still intriguing, but you cannot keep up. And when you have thousands of machines, strange things are bound to happen, and node failures and like memory errors, like very bizarre bugs are bound to happen. So I think in our systems, two things are fairly noticeable. One is tail latencies matter. I mean, I'm not the first one to come up with this, but I do observe it in a very accurate way. I do recommend a talk by, I think it was ISCA 2011 by someone from Google, Louise something. He talked about this as well. So when you do fan outs, if one of the shards is slow, your entire query will be slow. So that's why scale matters. Another thing is deterministic configuration. So Twitter is moving towards more like a container environment. Do you guys know Mesos? Yeah, so Mesos means you can schedule a job that does resource sharing on a physical machine. You can specify how many CPUs you want, how much memory you want, how much disk you want. And what the scheduler does is it fulfills a request, and there is a monitor. When you go over your resource requirement, you get killed. So that's actually a very high toll. If your service, I think this is one of my biggest quibble about Redis, is that Redis introduces external fragmentation compared to, for example, in Memcache, what you have is internal fragmentation. Right? Internal fragmentation means you store less data for the memory. External fragmentation means you use more memory for the same amount of data. But the importance becomes quite significant when we are moved into a container environment. Because now, if you don't want to be killed, you have to compensate for that by oversupply. You have to guess, I think my memory fragmentation ratio won't go over 5%. So let me just allocate 10% more as a buffer space. Or I think I will get 5,000 connections per host. But just in case there's a network glitch and all the connections are restarted, let me allocate memory for 10,000 connections. But this is not great. One, you have to be fairly confident that you've left enough buffer room. So when you are actually confident that you've left enough buffer room, you probably have introduced a significant amount of waste. Right? Like I wouldn't allocate just 10% more if I know the fragmentation is 5%. I probably will allocate 20% more. So there's a cost effect in there too. So another thing is shit happens. In a large cluster, bad things happen beyond your imagination. So even you think you're safe, there are cases where just behavior is unexpected. So if the service cannot degrade gracefully, by gracefully I mean if I say I will only use 10 gigs of RAM, and when I go over that, I reject any upcoming requests until I go under, that's very graceful. So you will fail a small percentage of the traffic that's proportional to the resource that they require. But actually, most service today cannot do that, right? So you guys probably all know about GC spiral. When you go over it, basically things just get dropped on the floor. That's not graceful, and that's actually a big problem that has been bugging a lot of teams in a lot of companies every day. So I would like to see a service that has very tight resource limit. If I say I'm going to use this much memory, that's it. I'm going to reject any future request that makes me go over, so that at least I can serve whatever I'm already serving. So that's another takeaway. Having peace of mind, knowing how your system would behave at runtime is really useful. And there was actually one case. Same latency story. So people were like, this actually was the reason I did the profiling in the first place, was people were seeing bad tail latencies, and they were like, your service is slow. So I have to do the benchmark to tell them the profiling. Actually, I did TCP dump and Wireshark and all that, and correlate the timestamps. But it was work. So imagine the tail latencies of the service is actually bad. So now you have your P29 on the client as, let's say, 50 milliseconds. But your tail latencies on the server at P39 is like 5 milliseconds. So you would tell people like, no, your tail latencies cannot be explained by my tail latency because the percentage don't match and all that. That would be a much harder explanation to do than just straightforward tell them my service is never slow. Right? This is actually quite a privileged place to be, to have confidence in the quality, in the SLA of your service. So, yep.
Are you right now running Redis on Mesos?
We are.
Yeah.
Yes, but so one thing on that, we actually run both Memcache with our fork. We use Memcache. We run both Memcache and Redis and Mesos, but given the Mesos way of doing resource policing, which is kind of like a counting system, right? Basically, Mesos checks how much CPU you've used in the previous time slot, and throttles a process if it goes over. And that checking period is actually 2 coarse grain for in a real-time system and for a service like cache. So a lot of us, our clients set timeouts at 20 milliseconds or something like that, or even lower. So if the check latency, if the check period is greater than 20 milliseconds, it doesn't matter, right? If someone else grabbed the CPU for 20 milliseconds, all of those requests timeout. So this is the one thing is that cache or very ultra low latency services don't really play super well with Mesos today. And even you do something like, let's say, CPU pinning, right? You use CPU set to dedicate a core. You still have the problem of soft IRQ from the networking stack. So unless you can isolate hardware resource all the way from NIC queues to CPUs, time sharing is going to be somewhat problematic. So we do use Mesos, but we try to isolate this particular type of jobs from the other jobs. All right. So my second takeaway is kind of an observation, and I think there's a lot to be done in this space, is to push computation to where the data is. I think actually Redis fits as an example for this, right? If you think about remodify write, it's basically treating the server as very dumb, just as data in-memory store. Redis moves this one step forward, saying we can do more than just giving you the data. We can, edit the data for you. I think Lua is another great step forward in that you can do not only just what the API tells you that you can do, you can also specify what computation you want. And you just do that on the server side because there's still CPU to have, and there's going to be more in the future. So I think the hardware trend makes it very desirable. So CPUs are becoming more and more numerous. The 32 cores on a server will be very standard very soon. The network bandwidth compared to, if is like on the order of tens of gigabytes per second. If you compare that to the bandwidth of the network I/O, we are still struggling with 10 gig links, and the software with 10 gig links are still kind of buggy. So most of our servers are still equipped with, just gig links, and the disk bandwidth is similar to that of network. Right? So if you compare all these numbers, it's actually quite desirable to do some computation before you store anything on disk, or do some computation before you push any data over the network if you can make it happen. And we, kind of the data insight project we did was another proof of concept that there are a category of applications that fit into that model, that you can do something before you send it over the network or store it. So basically I have a particular comment about Lua scripting in Redis. I think it's great. I think it's, when it was introduced a while ago, so it's actually great foresight. But I wouldn't consider Lua scripting production ready. And my reasons are because you do this on the fly. So you can store, so it's kind of like stored procedure in relational database. If you go ask a DBA, what do you think of relational, stored procedure? You will provoke some kind of fear or resentment, because it's kind of like running a Flash in your browser, right? It's slow, and because it's someone else's code, it's definitely terrible, right? It cannot be as good as yours, and also it brings everybody down with it. So all the requests that come to the same servers that run the store procedure potentially can be affected if the store procedure itself is slow. Same goes with scripting. If you allow on-the-fly scripting, pretty much all the service owners who have to maintain the SLA for the container or for the actual environment it runs will say no. I do not want to breach my SLA because you want to run just a silly little script, and then that will make me look bad. Why do I want to do that? So that's, I think Lua scripting has great potential, but I think the way it is run in production probably needs to change. So I don't really have a conclusion on this, but I think a deployed script would be a better approach to this. So if you say you can load Lua scripts as part of a configuration, there's now whoever owns the service has much better control. You can do code review, you can do benchmarking and profiling. You can tell them this is your throughput if you run this many times a second, and therefore you should allocate hardware resources accordingly. And also you can do other optimization, like you can use a compiler to compile the scripting to something that's native, right? So until then, I think Lua script would still be like a fun feature that you try on your own or test on a small scale. I would love to see it becoming more production friendly. And so the last thing is I just came up with this thought yesterday. So we, in our data insight, we use the Storm. Basically what Storm does is you set up like little pipes and you send messages to different destinations. And each destination would do some computation and forward that to the next one. Redis pretty much has all the components necessary, well, in an abstract level, not in a practical sense. Basically, there's the pub sub. You can listen to or send things over the pipes. You can specify how the routing happens, and you can have scripting. So why cannot Redis be the next high-performance stream processing? Like, I am fairly confident it will be better than Storm. Yeah.
In January, I did a little hack on top of Redis that lets you subscribe scripts to pub/sub channels. And I don't know if you've seen that, but it's out there and you can look at it and play with it. It's,
I would do that.
And it works. And you can even republish from inside scripts to make kind of trees of data flow inside of Redis.
I see. Cool. I would definitely check it out.
I mean, the difference is Storm is guaranteed delivery.
Yes.
Right? I mean, pub/sub is fire and forget.
That I would say, it's not a fundamental barrier. Like as it is, it's not the same.
Yeah.
The question of whether can you make it,
right.
okay. That's right.
So it would have to be a different qualified pub/sub in Redis.
That's right.
Yeah.
But this is a meetup. I'm just throwing ideas out there. I think this is a possibility.
Because you love Redis, but do you love Storm? I mean.
No comment.
I don't know.
So here's my wish list for Redis. I want explicit memory management. So, like, I'm not exactly a fan of 2M-cache or memcache, even though I spend a lot of time on that. But one thing I do like about it is I never have to worry about using too much memory. Well, unless you have too many connections, but that's much less likely. That's pretty much the number one thing. And deployable Lua script, which I just described, and multi-threading. Redis actually does, so the irony here is memcache is multi-threaded, but it does multi-threading in a pretty terrible way, which kind of makes it pointless to do multi-threading. And it doesn't even do that much computation. I've never had a single service which is like, no, I need more instances because the throughput isn't high enough. In our ecosystem, it's actually very hard to go over, say, 100K QPS. So the bottleneck often comes comes to either memory or network long before it hits the QPS threshold. For Redis, it's a different story. Redis actually does work inside the server, and it actually can benefit from multi-threading. But multi-threading is really hard, and I've debugged a few like racing conditions, and it's very time-consuming. So I totally understand why Redis doesn't do it, but if Redis can do multi-threading right, it basically makes Redis cluster easier to manage. So we have a lot of pretty tall boxes, by which I mean, each host would have over 100 gigs of memory and a lot of CPUs. So if we want to use the hardware resource fully with Redis, we need to spin up a lot of instances per physical host. So that means for a single cluster, if you have 20 cores, right? If you want to use all your 20 cores with a single threaded, process, you need to create 20 of them. So imagine a cluster that has 50 members and another cluster with 1,000 members. From a distributed system point of view, these are completely different systems with very different problems inherently. So the 1,000 node cluster will always be much harder to manage with more overhead when it comes to connection and all that, compared to a 50 node system. So I think, it's just wish list. You can wish for anything. And multi-threading would be on my wish list as well. So in fact, we've already started a project that pretty much is a combination of Redis protocol and the things I was wishing for. So, I'm not holding my breath, and, we'll see what happens with that. Which brings my last point, open source. It's kind of it's a very touchy topic, and it usually comes with controversies. And personally, as someone who has a pretty bad record of basically stealing people's source code, forking it, and then releasing it as our own branch, and be like bad players in the community. I want to say, basically, what happened? Why did we fork? Why did we refactor? And why did we rewrite instead of working on top of trunk? I think there are 3 factors into play here. And in the end, it boils down to, with open source projects run by the community, it's hard to meet all 3 of them. So the first one is context. By context, I mean, so one example of context would be scale. So if you run a service with 10 instances, it's very different from running it with 1,000 instances. So you would be facing different problems, which means you may have different priorities. So priorities can be a result of the particular context you face, or could be what your company does. Like for Twitter, we want really low latencies on our particular, request path, because we claim to be a real-time, messaging system or something, right? If your company is like pipeline analytics, then you are not so sensitive to latency. So you don't care about the improvements on latency as much. So you probably won't allocate resources on that. And the last thing is quality. I think, sadly, my personal experience that if you want a code base that has very high quality code, you kind of have to have some clandestine figure behind it that keeps control of the quality. I would say, Enter is such a person for Redis. He makes sure no bad code gets checked in, even though some people may want their features really bad, right? If it's bad code, it's not in. Same goes with Nginx, right? This one guy basically makes sure all the code in Nginx is good, and Nginx is a great source repo. We keep stealing code from there all the time. But what I mean is, if a project is basically loosely maintained by a committee that otherwise don't really have tight connections, it's actually not that easy to enforce good quality, and things like refactoring pretty much can never be done collaboratively. For example, Torrent proxy. Torrent proxy, as I said, was built for Memcache. And then it was the Redis support was added later. So if you look at some of the basic data structures, like the request data structure, there are things like a Redis flag, right? Is this request a Redis request? If you apply some, software design principles to it, you'd be like, this is not a very generic solution to supporting multiple protocols. You probably should abstract out the protocol relevant part and just stack it on top of a generic, request handling module. But who's going to do that, right? So these are things. I think. So basically, all the projects we ended up forking can be explained by one of those reasons. So basically, and the C projects are especially bad. So if you have a Java project, you can load a class. If you don't like a particular member of it and it's not final or it's not protected or anything, you overload it. A lot of things you can plug in the last minute when you are ready to run a launch. C is not a modern language. It supports you to do that, like namespacing, all that things are lacking. So what happens to a lot of C open source projects is that there's actually a lot of sharing and reusing of code. But unless someone say, I stole this B-tree implementation from BSD, you won't know it. It's just, if you don't look at it closely, it's just an integral part of the project. So I think there's some inherent difficulties about sharing C projects, but I don't know what is a good solution for that. So basically, personally, I really want to be a better player in the open source community. There's just all these limitations, and I would love to hear your opinion about how we can do better. So that's pretty much it. And I'm open for any questions. It doesn't have to be Redis. You can ask me anything that you think I may have knowledge of.
But so you're still running Redis 2.4 fork?
Yes.
I mean, your own fork?
Yeah, there are things I want from later versions,
Right,
but
yeah, I mean that's.
yeah.
I mean, at Flickr, it has been very painful to get to 2.8. But I mean, I've got a prototypical recommendation service I just put on 2.8, and it's just a delight, when I go back to the old ones that we just haven't prioritized moving off of like 2.6.
Right. So that's one motivation for us to contribute back, right? Once if I submit this pull request and the hybrid list, if it gets merged into trunk, now at least on that cluster I can run trunk. If I submit B-tree and that gets merged, I can run the top version. So
Do you have other use cases where you are using just standard Redis, or are you saying is that on more an experimental or not your group?
We don't, unless people are doing that at a very small scale that even don't require our support, we don't have any use cases of other native features.
Can you talk more about the implementation of the hybrid list? How did you how did you tune the size of the zip list? Is that still near the recommended size, or were those changed yet?
Oh, good question. I did, so because I only have to optimize for this one case, which is timeline, right? So I have existing latency measures and all that. So basically we did, we set the threshold at different, basically you can have very wide strides of different setups. So I would do, starting as little as, let's say 2K, and you can go over 20K or 200K, however you want to set it. And then you just compare that to using straight up zip list or straight up linked list. And basically what you want, the bigger the better, the less memory overhead. The smaller, probably the easier to alloc. So you want the smallest size that doesn't introduce higher latency. And we've actually found that. So I think this tuning probably would be done on a per use case basis. And we did that, and we didn't lose any performance. So that's how we did it. And the number we chose was actually at least order of, I don't remember the exact numbers, but basically each chunk was an order of magnitude smaller than the largest list we had before. So that basically got rid of the heavy allocation problem we had. Yep.
You kind of enumerated the reasons for the fork, kind of separating from the community. What are the barriers for actually going and submitting the pull requests to kind of, share it back with the community? What are the kind of big reasons why you didn't do that?
Yeah, resource. Well, laziness really, but resources. So the thing is, I'm paid by a company. I have an obligation to make something that works for the company. I don't have an obligation, not directly to the community. So if I spend time on merging a request upstream, I risk delaying my other obligations to the company. So it's fairly realistic, right? If you have a good manager, I think Enterprise is really lucky, and he's doing a really good job. He gets paid by a company to do whatever he wants. This is so rare that I really envy him. But realistically, unless a push from the community saying, public pressure can help these things happen sooner. The community can be like, you benefit so much from Redis, you should contribute to, right? So that's good in theory. Practically, I think we lack measures to make the companies, like Google doesn't pay for SSL, right? It's benefiting tremendously from the library. I'm not sure, I don't have the answer to, yeah, go ahead.
I mean, you can point to things like Heartbleed and how they kind of, obviously contribute a lot back to identifying that issue. So
Right.
I don't know. It's a tough question for open source, and like, what's the right way to get kind of people on the corporate side to kind of give back? I don't know what the right answer is.
Right. So I think I don't have any answer at all. But a lot of companies do open sourcing for several reasons. Like marketing is one of them. Like we're painting a good image for the company. Again, all personal view. Okay, don't take it on Twitter. And another thing is recruiting, right? If you identify people who are capable of working on the project that you find valuable, you can try to hire them. Another one is kind of like beta testers or bug finders. By exposing that to more use cases, you can find certain issues sooner. So I think the reality is a lot of companies do have dedicated personnel to open source. But that person is not the people who are in charge of the roadmap. Like my manager is not open source. It's not a part of his job to do open source, and not near the top of the list. There's another person. I think the community can work with that person, like Twitter has a team that does open source. I think building a connection with big companies or semi-large companies about open sourcing certain things and actually gets the entire communication through to the people who actually make the roadmap will make a lot of things easier. Like I would love to say this quarter's goal is just for me to make sure that these changes get merged, or that I release this particular change so that it can be shared by the community, and just rip out all the company specific part of it. I would love to have time for that, but reality is, software engineers are often overwhelmed and have other things piled on top of that. You go first.
In case of adding more nodes to the proxy, you mentioned you were doing some kind of rebalancing.
Yep.
Can you go into detail a little bit? What's the, do you have another translation layer between
Yes.
address and nodes?
Yes.
What type of address? Is that a hash? Of the
Yeah, you can think of it as hash. So if you map all your keys to integer, 32-bit or 64-bit integer space, then every integer can serve potentially as a bucket, right? The number of buckets can be arbitrarily large or small. If you have a bunch of integers, you can divide them however you want. And in the end, the allocation process basically boils down to mapping these buckets to physical nodes. So basically, every shard will be aware not directly of the keys they own, but of the buckets they own. And routing happens, the way you do routing is you map a key to a bucket. And then by association, you know which physical server owns that. So basically, the mapping from the keys to the buckets doesn't change when you add or remove a node. What changes is the association between buckets and the physical nodes.
But wouldn't that require rebalancing?
Yes.
You do that?
Yes. So you basically you don't. That's why you still it doesn't. This means you still can only do rebalancing somewhat slowly, right? You don't want to move too many shards at the same time. Storage system has the same issue. You don't want to move too many shards at the same time.
So you figure out which bucket you go to on the app side? Because you say, I think
On the proxy side.
Because of the proxy manages that?
Yep. So the proxy basically, clients see proxies as stateless. You can talk to any one of them. Yep.
So the data is not sharded and replicated. So your data is not replicated. One bucket is not replicated.
It can be done. Again, it's done in the proxy. So you can basically map one bucket to two shards, one bucket to two physical instances.
On the right will go to both.
Yeah, this is a policy that I think people using it need to come up with. You can do, for example, you can replicate writes and read from one. You can replicate, basically you always want to replicate writes. You can read from one, you can read from both and compare and do a repair, right? If one of them is missing or one of them is old, if you have such a mechanism. So that's more like a configuration policy.
Okay. My question was, if you don't have replication, how does a failure impact your SLA? I guess failures are fairly common.
Yeah, sure. So the most straightforward way to do it is figure out what's the likely case of failure. Like losing one rack of machines is highly possible because you may lose power to one rack, or the rack top switch may fail. So so basically that's our bare minimum failure case, and we would allocate enough resource in the backup tier. For example, if you're using Redis as cache and you have another database, your database need to be able to absorb the fraction of requests that corresponds to one rack. And there are other things when you allocate resources, there are other things you consider, like I don't want to allocate too many instances on one rack because that significantly increase the number of, increase my failure domain, right? Failure domain is defined as the percentage of request. So if you do all these steps, basically you can come up with a tiered configuration that's reasonably robust. So in the common cases, you won't have visible SLA breach. So you just absorb it in the backup tier. You over allocate your storage system to absorb that. And there are other things you can do, right? Facebook did it with their memcache pool in that they have, what's the name for that? They have kind of like a temporary spillover pool. So what happens if you lose, say I have 100 shard, and I will have, say, 5 backups sitting, just idling. If one of these 100, basically it's almost never happened, it has never happened that more than 5 of them would fail, which is not too unreasonable. So what happens if I detect one of those 100 primaries failed, I would pull in one of the backups as my secondary tier, and you treat it differently. So you would have a much shorter TTL when you go to your secondary tier, so you don't have too much stale data. So when your primary comes back up, you stop sending requests to your backup pool, and the data cleans themselves reasonably quickly. So that's another way of doing it. So tiered caching is actually very, very useful, which is something actually after we found out how common hotkeys are in our systems with the Data Insight project we did, we're basically building a client-side caching that we stuck into everybody's client, so it automatically caches hotkeys for you, so we don't get like DOSed. Yep.
Take one more question, and then give one more question.
Yeah. Okay.
So internally, how do you guys, as far as like the cost of, since you guys operate cache as a service,
Yep.
more or less?
More or less. Yep.
How do you guys manage, as far as like what the benefits of cache for different keys or whatever it is for what they're caching and the cost of actually looking up the cache? Are you providing analytics back to the whatever project's implementing it, or is that up to the project owner or them to figure out like what they should cache and what they shouldn't?
So realistically, it is left to the project owners because we cannot audit. We cannot keep up with the user requests, and to gain the right insight to evaluate someone's caching and come up with really good configurations is actually not trivial. So the analytics project helps, like unique keys, right? You shouldn't go over that. There's no point going over than the data you actually need. But there's a cutoff somewhere. You probably, on the other hand, you probably don't want to cache everything. You probably only want to cache things you will visit, right? Things you visit once by definition shouldn't be cached. For that kind of thing, I have to say, ideally we want to get there, but we're not making enough progress to make it happen now. So, the strategy we've taken is we pretty much let you get a free pass if you are small, right? If you only want like 100 gigs of memory, which is like one machine, just do whatever. If you use 5% of a resource, so be it. But if you're really big, if you're like 1,000 node or 500 node, we will work more closely with those big users We just let the long tail do the thing.
Cool.
All right.
Thank you. You have one hand.